Okay, so let's continue with our lecture on the linear applications for op-amp. So the first application, there are 5 applications altogether that we're going to look at, as you've seen in the previous video. So we're looking at the inverting, non-inverting, follower, subtractor, and summer. Okay, so these are not covered. Okay, so let's look at the first one, the inverting amplifier. So in the inverting amplifier, we have the signal input applied to the inverting negative input. Okay, so we have the signal applied to the negative. Okay, so it's very important to put your input connected to the negative through a resistor R1. Okay, and another characteristic that we have to know and to see is we have a positive terminal. The non-inverting input is connected to the ground terminal. Okay, so remember we have a virtual ground. We have a virtual ground, which means that if V here is equal to 0, so V plus, so V plus equals to 0, so our V negative is also equals to 0. Okay, so we have a virtual ground, so both are 0. We have a feedback resistor RF. We have a feedback resistor RF connected in a negative feedback. Okay, so here is a negative feedback, you can see. Okay, so this is what it means by the feedback or the closed loop configuration of the op-amp. Okay, so we have the feedback, we have all the connection, and this particular connection like this is called the inverting amplifier. And why it's called inverting? Because it's amplified and it's going to invert your input signals on the output. So here we can actually prove that actually V out here is simply equals to negative RF over R1 times VI. Okay, so and we see the inverting here, we have a negative there. Okay, so the magnitude of the amplification is in fact the ratio between RF and R1. Okay, so how to prove this? We can prove it in the next slide here. We can see that this is the inverting, so we can see V in negative. We have a negative feedback, the plus to the ground. So immediately we know it's an inverting amplifier for this configuration. And we see that here that no current can go through here. This is infinite R. Okay, so R is infinity in the input of the op-amp, and therefore no current flows in. Okay, which means that your I1 is equals to I2. Okay, so I1 is equals to I2 since no current flows in. Now, what is I1? So I1 here is simply V in. And here, because we have virtual ground, so this is 0, and therefore here is also 0. Okay, so I1 is simply V in minus 0 over R1. Okay, just a simple current calculation there. And then I2 is going like this, so it says 0 minus V out over R2. Okay, so we have I1 and we have I2 that we have derived from the analysis, and we know that I1 equals to I2, and therefore your V in over R1 is equals to minus V out over R2. Okay, by looking at these two together. Okay, and therefore we can derive V out is in fact will be equals to the equation here, which is simply here is minus R2 over R1 times V in. Okay, so this is an equation that we need to know, this one, where your V out is just a ratio of R to R1 inverting times the V in. Okay, let's look at the next one. So the next one is the non-inverting amplifier. So the non-inverting, the characteristic is that we have now, we still have a negative feedback. Okay, negative feedback like this. Okay, on the inverting side, we put the resistor, it's called a negative feedback. And here we are going to put V in on the plus. Okay, so a little bit different than the inverting amplifier. The non-inverting, we have the V in on the plus. The inverting, we have the V in on the negative side of the input. So V in on the plus, and therefore we have a virtual ground if this is V in, and therefore here is also V in. Okay, and no current flows through the op-amp because infinite resistance, and we have the current on the output side. Okay, we have the current on the output side, and because of the infinite resistance, and now we have I1 equals to I2. Okay, I1 is approximately equals to I2, and what is I1 and I2? So we can derive here that I1 is simply V in over R1. Okay, looking at this and here, V in minus 0. Okay, V in minus 0 over R1, and then we have I2. Okay, I2 is simply V out minus V in over R2. Okay, so if we equate these two together, we have V in over R1 is equals to V out minus V in over R2. Okay, and then we can derive the V out value. Okay, and V out, if we do some mathematical manipulation, we should get V out is equals to 1 plus R2 over R1 times V in, and this is the equation that we need to know. Okay, which is given here. Okay, so for a non-inverting amplifier configuration, negative feedback, we have V out is equals to 1 plus R2 over R1 times V in on the input. Okay, so V out here we take here. Okay, so that's number 2. Let's look at the next one, number 3. Number 3 is the simplest one. Okay, number 3 is the simplest one. It's called the unity follower. Unity follower, we see here that if here is V in, and because of the virtual ground, and here is also going to be V in, and therefore your V out here is going to be equals to V in. Okay, so in actual fact, what we have is actually V out equals to V in, and so the question is, why do we want to have V out equals to V in, when in fact we can just simply make a wire, okay, a wire like this, V in, and then here is your V out, so basically on the same line. The reason is because, for example, and here it says, due to the infinite input impedance of the op-amp, no current can be drawn from the circuit before V in, thus this part is isolated. Very useful if you want to interface with sensors such as microelectrode, microphone, etc. Okay, for example, if we have a feedback here, we have a microphone. Okay, and the current sort of like goes through here. Okay, is it going to impact the input? It will not impact the original input. Okay, it will not give a feedback. Okay, so this will not travel to the original input. So it's sort of like a barrier. Okay, so this is number 3. Number 4 is the difference amplifier or the subtractor. So here also we can actually do some mathematical analysis, and we can derive what is V out of a function of V1, V2. Okay, so our input is V1, V2. So what is the function of V out in terms of the input V1, V2, and also R1 and R2. So it gives here that if you do the derivation, you will get V out is equals to V1 minus V2, which is the difference. Okay, V1 minus V2 is the difference, times R2 over R1. Okay, so how to prove this? Just some analysis here. We can say that, let's say here is Vx. Okay, some value. It is not 0 now. It's not connected to ground. And because here is Vx, due to virtual ground, we also have Vx on the negative side. So both sides we have Vx. So can we derive Vx here? So the first Vx here on down here is Vx is simply the voltage across R2 is V1 R2 over R1 plus R2. Okay, so just a voltage across R2 for given V1. So that's the first Vx. And what about the second Vx here? So for this one, we have the current here I is going to be I1 is going to be equals to the current I2 going like this. Okay, because no current flow in the op-amp, and therefore we have V2 minus Vx, okay, over R1 is equals to Vx minus V out over R2. Okay, so the current V2 Vx R1 is equals to Vx minus V out over R2, and here we can derive our Vx equals to something, okay, in terms of V out, in terms of V2 and R1, and then we can equate Vx1 and this one Vx2. So Vx1, call it Vx2. So Vx1 is equals to Vx2, and then we can derive V out, okay, by equating the equation Vx1, okay, and Vx2. So here is our Vx2 actually. Okay, so equating the Vx1 and Vx2 together, we're going to get V out is in fact V1 minus V2 times R2 over R1. Okay, and it's actually a difference amplifier or the subtractor. Okay, so let's look at the next one. The last one, which is the summing amplifier. Okay, the summing amplifier is just going to sum the input voltages. So in this case, to analyze this circuit, we say there's a current I at the node there, and the current I there is actually equals to I1 plus I2 plus IN and so on. Okay, so it's just a summation, Kirchhoff's current law, whereas the total current at this node here is just a summation of I1, I2 and so on. Okay, so from here we know that I1 is V1 minus, this is 0, so here is V1 over R1, okay, plus V2 over R2 plus Vn over Rn. Okay, so it's just a summation of the current, okay, V1 minus 0 over R1 plus V2 minus 0 over R2 and so on. And we know that this I will be equals to this I, okay, the IF is equals to IF, and IF is minus V out over RF. Okay, so 0 minus V out over RF. So if we have this, can we derive the value of V out? So yes, we can. So V out is just going to be minus RF times V1 over R1 plus V2 over R2 Vn over Rn. Okay, that's given here. Okay, so this is the value of V out, and if R1 equals to R2 equals to Rf, therefore we have V out is just the summation V1 all the way to Vn. Okay, so this is a derivation, but we need to know basically this equation here is very important. Or the one that we derive here is V out is minus RF V1 over R1, okay, plus V2 over R2 plus until Vn over Rn as given here. Okay, and then we also have a non-inverting. So here is the inverting. Here is inverting because you have a negative. Okay, so it's an inverting summer in fact, and we can also have a non-inverting summer where if you were to analyze this, we see that here is your V plus, here is your V negative, where V plus equals to V negative. And looking at this, we know that from our non-inverting configuration, V out, okay, V out is just going to be 1 plus RF over R1 times V plus. Okay, V plus can say is also there. Okay, because V plus equals to V negative, so V plus is also up there, and V out here is just going to be this one in terms of V plus. But then what is the value of V plus there? The value of V plus there is a two component across RB and RA, where V plus can be defined as follows, where V plus is just VA across RB, okay, VA across RB, and then VB across RA. Okay, you sum these two together, you're going to get the V plus. So if we take this and put it inside there, okay, so we take the V plus, put it inside there, we are going to get this equation. Okay, so here is your V plus. Okay, 1 plus RF over R1 times the V plus, which is this one. Okay, so that's we can do a detailed derivation of this, but basically this is what you need to understand, the equation for summing amplifier non-inverting. Okay, so let's do a little bit of exercise here, where there are many op-amps here. There are 5 in fact. Okay, 1, 2, 3, 4 and 5 operational amplifier right there, and we want to name the function of each op-amp. Okay, name the function and want to find what is the voltage at Vout1, Vout2, Vout3, Vout4 and Vout5. Okay, that's quite a lot, so we have to find the voltages at 5 nodes and also the name of the function. So for number one, so we can see that the plus, okay, is connected to the negative here, and then we have the V in on the positive, so clearly we can see this is called the inverting amplifier. Okay, it's called the inverting amplifier. That's the name. And what is VO1? So VO1, if you remember the equation, it is simply negative 2k over 1k times 2 volts. Okay. So here you should get negative 4 volts. Okay, so this is the equation for your inverting amplifier. And then what about number 2? So number 2 we have this is the simplest one. So here is 2 volt. 2 volt. This is number 2. It's called a unity follower. It's called a unity follower, whereby your VO2 is simply equals to 2 volts. And number 3. Number 3 we have the input on the positive side, and we have negative feedback to the ground, and here is called the non-inverting. Okay, here is called the non-inverting amplifier. And what is our Vout3? So according to our equation, okay, here there's no current flow. Okay, so I here equals to 0. So if no current flow to the op-amp, and therefore no voltage drop, okay, no voltage drop because the resistor, therefore the voltage here is going to be 2 volts. Okay, so if this is 2 volts, here is also 2 volts. Okay, and if you remember our equation, this is simply going to be 1 over 1k over 1k, okay, times times 2 volts. Okay, so this is going to be 1 plus 1 is 1, 1 plus 1 is 2, okay, 2 times 2 is 4 volts, okay, non-inverting. Okay, number 4, we can see that we have Vout1, Vout2, Vout3 with a negative feedback, and this is called the inverting summer. The inverting summer. Okay, so in the inverting summer, your Vout is simply going to be negative 2k. Okay, Vout1 over 2k, so Vout1 is negative 4 over 2k plus Vout2 over 2k, so Vout2 over 2k plus 4 over 2k. Okay, and here we should have 2k here we can cancel out. Okay, and here we have going to be negative 2 volts. Okay, so 4 minus 4 cancel out, we have 2 times negative 1, we have negative 2 volts. Okay, and finally number 5. Number 5 looks like also the inverting summer. Okay, so let's look at the fifth one, number 5. So number 5 is a little bit different. So for number 5, you see a combination of inverting summer and the non-inverting summer. Okay, the reason is because we have the positive connection, okay, the positive V plus connecting to 2 voltage sources, 2 volts, that is the non-inverting summer, and then we have these 2 connections here, which is going to do the inverting sum. So it's a combination of inverting summer and the non-inverting summer. And the first step is to calculate your Vx here, where you probably have to derive yourself. that if you do the derivation as shown in the previous slides, you are going to get Vx is equals to 2 volts, okay, which is just a combination of these 2 volts together. Now, if Vx is 2 volts here, then here is also 2 volts on this node here on the V minus. So if you have a 2 volts on the V minus, now it becomes an inverting summer. Okay, so an inverting summer on 2 volts there will simply, if you do the analysis, we are going to see that actually that 2 minus V out, okay, 2 minus V out over 2K, okay, which is the current here, is going to be the sum of these two currents together. So it's just going to be V out 4. So V out 4 we calculated as here, V out 4 is -2. So it's -2 divided by 1K plus 6 minus 2 divided by 2K. Okay, so the summation of this current and this current is going to be equal to the output current. So here, if you do the analysis here, we have all the constant value here. Okay, 1K, and try to take out V out. So if we able to take out V out, we can see that V out is in fact going to be 6 volts. Okay, a combination of inverting and non-inverting. Okay, so you can try and prove yourself that V out here is actually equals to 6 volt by doing some mathematical manipulation. Okay, so that's all for this week's lecture, and next week we'll cover the non-linear applications for op-amps.